Now we move to a presentation on another technology important for reducing emissions, which is going to be presented to us by Jeff Diestelmeier, who is Chief System Designer at Watlow. His topic is the development of robust exhaust heating systems for medium-duty diesel vehicles. Just to give you some background, Jeff has held his current position, Chief System Designer for the last year. Before that, he was responsible for other areas of the business strategy and product development. He's responsible for developing breakthrough thermal technologies for improving engine and after-treatment system performance, which is a topic we've heard about all through today, managing heat in the exhaust system, after-treatment system. Previously, he worked in aircraft engine system division of Woodward Governor Company. So an interesting background. But yes, the topic is going to be focusing now on what can be done to manage exhaust heating systems, to improve NOx reduction in the SCR systems we've heard about earlier in a fuel-efficient manner. So over to you, Jeff. Thanks for joining us. The floor's yours.
Thank you, Tim, and good afternoon, everyone. For the presentation I'm going to share today, it's based in part on a paper that we presented at the SAE World Congress a couple of months ago in Detroit. And I would just like to acknowledge the co-authors, David Culbertson and James Pradon, both from Watlow, and then Dr. Magdi Kher from Mag Diesel Technologies. This is an outline, just a brief introduction to Watlow, the company, the motivation for our work, talk a little bit about the need for heat in these diesel after-treatment systems, various methods for heating the exhaust gas, some work around an initial electric heater design and testing that we did with that unit, and then showing the evolution to a new 24-volt heating system design and some conclusions. A little bit of a background on Watlow. Our core purpose is enriching the lives of others through inspired innovation. We've always been a technical-based company, and we typically are the ones that try to solve some of the toughest thermal problems. In every one of these applications here, there's a difficult thermal challenge behind the scenes, whether it's diesel after-treatment or the production of complicated electronic circuitry or medical devices or what have you. Our company is privately held, third generation, family owned. We're headquartered in St. Louis, Missouri, and our CEO, Peter Deloge, is actually the grandson of the founder of the company. We're probably going to be over $400 million in revenue in 2017. 45 sales offices around the globe, 11 manufacturing facilities, 3 technology centers, including one based in Austria, and over 2,000 team members worldwide. With regards to the diesel business segment, we have well over 30 years of experience, and our products include heaters and temperature sensors for a wide variety of on-engine and after-treatment applications. And we're involved in virtually all of the market segments except for passenger cars. And we welcome you to stop by our booth over the next couple of days and say hello, and we'll be glad to go into more detail about our products. All right, the motivation for our work is really this fundamental challenge of trying to improve diesel engine efficiency while at the same time meeting more and more stringent emissions limits. And I think our speakers this morning all touched on this and did a really good job of highlighting this focus on CO2 reduction, improving the fuel economy, while dealing with tougher NOx requirements, whether it's RDE in Europe or the ultra-low NOx that CARB is pursuing. So the challenge is, how can we meet both of those needs? To understand that a little bit better, we just maybe spend a couple minutes and talk about the concept of heat engines. And a heat engine is really in the business of converting chemical energy to mechanical energy. So we put fuel and air. The fuel is chemical energy. We put air in as well, and we combust the fuel. And then we get a certain amount of work done by that engine. and then we have some losses to deal with. And so one of those losses is through the cooling system, and another primary category of losses is through the exhaust system. And as we again heard this morning, the efficiency of the diesel engine, which is probably one of the most efficient internal combustion engines that we know, is in the 40 to 45% range with aspirations to try to get to 50%. And so as we continue to raise that level of efficiency, we're going to have less and less waste energy in the exhaust system to heat the aftertreatment system. So the diesel engines, by their nature, are more efficient, and therefore they have lower exhaust temperatures than a petrol engine. But that low temperature doesn't help us much when it comes to NOx conversion. And we know that catalytic NOx reduction works well at higher exhaust gas temperatures, and you can see that on this chart here. As the temperature gets higher and higher, the conversion efficiency gets better and better. But really all three of the SCR catalyst formulations that the market knows today all suffer from poor performance at lower temperatures. And the RDE tests, where we're going to have to demonstrate under low load conditions that we're still in compliance with the emissions limits, put pressure on that, and also the ultra low NOx requirement that CARB is pursuing of trying to take the limit down to 0.02 grams or in that neighborhood per brake horsepower hour. You're going to need very high conversion rates under low temperature conditions. So all three of those formulations suffer from that problem. And you can see from the chart that depending on the catalyst, temperatures ranging from about 200 to 350 degrees C would certainly benefit NOx conversion during cold start and warm up. So when it comes to warming the aftertreatment system, there are two technology pathways to consider. The first one I'll call engine-based, and the second one I'll call exhaust-based. So the idea behind engine-based is that we use mechanisms on the engine to try to drive heat from the engine down through the exhaust pipes and into the catalysts that need that thermal energy to do their job. As compared to the exhaust-based methods where instead of trying to make the engine be the heat pump, we're going to place a heat source downstream much closer to the point where it's needed and then provide that thermal energy. So in this example here, I'm showing an electric heater as one of those exhaust-based methods. So with respect to the engine-based methods to increase exhaust gas temperature, there's a number of tools in the toolkit that an engine OEM can use. Some of the more common ones would be like intake air preheating or intake air throttling. Exhaust gas throttling is another common one. We also see late post-injection of fuel. Some people use cylinder bank cutout and cut out a certain number of cylinders to try to make the remaining cylinders work harder. And all of these measures, regardless of which ones we choose, all of these measures are going to consume an incremental amount of fuel in order to create that heat downstream. There's no silver bullet measure. In other words, there's no one of those measures that can do the job completely and perfectly. Each one of these measures are potentially able to be combined with one another to intensify the effect. But each one of them also comes with its own set of challenges. Some of them can adversely affect engine durability, for example. And most, if not all of them, fail to reach catalyst desulfation temperatures, which are quite high. And most, if not all of them, are unable to prevent urea deposit formation in the SCR system. Now, switching over to exhaust-based methods to increase temperature, these are the primary pathways. We have the ability to put an electric heater there. We have burner systems that can do that, and we also then have the hydrocarbon dosing, or some people might call that a catalytic burner. And all of these measures consume an incremental amount of fuel as well. And which ones we choose really comes down to what is the cost, what's the effectiveness, the durability, and the serviceability to support the technology. Here's an example of a burner system. This is Caterpillar. which used a burner system in the on-road engines when they were still in that business, and continue to use a burner system today in the off-road market. The challenge with the burner systems are keeping the flame lit. Is when the filter starts building up some soot accumulation, you get a back pressure, and it's difficult to keep that flame lit, so you have to have a separate air supply, and there are other issues associated with it as well, not the least of which is the cost. This is an example of hydrocarbon dosing. The industry is quite familiar with this method, where we have an injector. Oftentimes we call that the seventh injector in the exhaust pipe, or we can do that late post-injection in cylinder dosing. We have a DOC, diesel oxidation catalyst, and when that fuel comes in contact with the DOC that's properly warmed up, then we get the exotherm and create the energy that we need in the system. And the other alternative then, as I mentioned, is the use of an electric heater. And an electric heater places the heat directly in the exhaust, and it's a relatively simple concept. We have a resistive element, a heater wire, and we apply a power across that heater. And the power that we apply depends on what kind of a temperature rise that we'd like to see on the outlet side of the heater. So the inputs to that is the temperature of the exhaust coming in and the mass flow rate of that exhaust. And then we have to multiply that by the coefficient of, or the specific heat of the exhaust under constant pressure. And so that equation there represents the relationship to determine the power of the heater required to achieve a certain delta temperature. And we also have to take into account the thermal efficiency of the heater, and that's really the losses of the heater to ambient surrounding it. So that value is typically about 0.9. Now I'll just describe a little bit of work that we did a few years ago with a prototype heater. And this heater is capable of operating at various settings between 12 and 30 kW of power. It's about 10 liters in volume. And we tested that on a 6.7 liter Cummins ISDE engine that was suitable for a hybrid electric application such as a bus. We loaded the engine with a dynamometer. We had a power inverter to convert AC power to DC power for the heater. And we placed the heater in the system directly upstream of the DOC. And then we had temperature sensors at various locations in the system, as you can see in the diagram there. So looking at the heater in a little bit more detail, inside the heater were 5 spiral wound elements, and each of those were 6 kW, so 30 kW if we had all 5 of them on. And the minimum power setting was 2 elements, so we could go 12, 18, 24, and 30 kW. And there's a view of the heater there when it's powered up on the right-hand side. Looking even further into the heater and the construction of the heating elements themselves, we have at the core, we have an electrical resistance wire, and this is typically a nickel chromium alloy. And when we apply electricity through that wire, we get the heating effect. Surrounding the wire, we have magnesium oxide, which is a mineral insulation, and then we have an outer sheath. And the idea is to take the thermal energy from the wire and transfer that thermal energy to the sheath, and then from the sheath to the exhaust gas. The MGO, our mineral insulation, really serves 3 functions. The first one is to isolate that electrically, that coil. The second one is to protect the resistance coil from vibration by means of dense compaction around that wire. So if you think about putting a heater on a vehicle, whether it's an on-road or an off-road vehicle, it's going to be subjected to a lot of vibration, and we want to make sure the wire doesn't get destroyed from that vibration. And then the third function of the MGO is to help conduct the thermal energy from the resistance coil to the sheath. We control the heater to achieve a target exhaust gas temperature, but we also need to be concerned about the internal temperature, or the temperature of that resistance wire, and we cannot let that exceed a certain limit, or the wire will eventually melt and the heater will stop functioning. So testing that heater on that diesel hybrid electric system that I mentioned, this is with the heater set at 30 kW, and we were running an FTP cold start cycle, and we were just trying to apply the maximum amount of heat that we could to the exhaust for the first 400 seconds of that cycle. And the part that I'll call your attention to, I'd like to call your attention to on this slide, is really this line right here, this kind of this reddish magenta or maroon color, and that's a function of the heater power. So we were trying to just apply the maximum amount of heat out of that heater, but when we reached a certain point, at about 150 seconds or so, the heater had to start cycling on and off because we were approaching that danger limit of the internal wire for the heater. So we had to cycle on and off, and you can see a number of times there in that 400 seconds the heater had to be turned off to protect itself. That same heater at the 12 kW setting, so powering up 2 of the coils inside of it, throughout that 400 seconds, again, the same cold start cycle, trying to just apply the maximum amount of heat. You can see, looking at that same line, that the heater never did reach that danger point and was able to remain on the same amount of time. So when we look at all of the tests that we did for that first 400 seconds at the various kW settings, we had at 30 and 24, the heater was limited by this internal temperature concern, and so we did not average 30 kW out of the 30 kW heater. It was just a shade under 25, and likewise, we did not average 24 kW. It was just a little bit over 20 because of this internal temperature consideration. So despite the fact that we had a heater of 10 liters volume, we were limited by this phenomenon. So we looked at that heater design and said, okay, we've learned a lot from that, and we learned enough that we created a product for highly electrified applications, mainly those that are truly diesel hybrid electric. So whether it's marine or a diesel generator, for example, would be a good example of this. We created this design, and we have this heater over on display next door. You can take a look at it on the break if you'd like. But looking at that product, we still weren't satisfied because it's bulky, it's costly, and it wasn't really suitable for an on-vehicle application with respect to vibration resistance and so forth. And also because it was really designed for high voltage, not the kind of voltages that you're going to have on a mobile vehicle. And so we focused a lot of energy around creating a much smaller, more compact heater that had low voltage capability. And the idea was for medium-duty, heavy-duty vehicles. And so this is the latest evolution of that heater design. And you can see it's a much smaller package size. So it's only about 2.5 or 3 inches in width, about 5 inches in diameter, and capable of being placed inside of the after-treatment system for the customer. So we've eliminated the exit and entry cones. We've eliminated having a separate can for the heater itself. Now that heater is a wrapped corrugated design, and we did a lot of work with that design trying to create a multifunctional purpose around it. So the first reason that we have that corrugation is to create a desirable natural frequency with some damping in order to improve the vibration resistance. And also what that corrugation does for us is it enables better thermal conductivity from that outer sheath of the heater directly to the exhaust gas. So effectively we increase the surface area of the heated metal, and we dissipate heat from the sheath much more quickly. So down below is a CFD analysis of that heater with a corrugated support and without the corrugated support. And the corrugations actually lower the sheath temperature by about 275 degrees C, which is a lot. So what that does is it enables us to drive the heater much harder, dissipate more thermal energy into the exhaust, which is a good thing, and gives us a lot more margin with respect to that internal wire temperature. And then the last function of the corrugation is that it does provide some mixing of the exhaust as well. Going along with that heater then, if we're working with these lower voltages on a vehicle, we also have the challenge of controlling that heater and switching power to it. And so we've developed a 24-volt smart power switch to go in conjunction with the heater to make a system. And that power switch is capable of 300 amps. It's a dual switching circuits. It's 105 degrees C rated hardware, and it has power measurement capability to capture heater voltage and heater current. It's got a heat sink to mount it on the vehicle frame, and then it is J1939 communication enabled, and it's able to then take information that the ECU is putting on the CAN bus and then in turn control the heater and the exhaust system and then communicate back to the ECU. So the smart power switch helps us protect that resistance wire while enabling us to rapidly heat, especially during transients and cold start operation. So the heater packaged, the idea of being able to package this inside the aftertreatment system reduces the cost, and we have a much smaller footprint, so it's suitable for use on a vehicle. And then it also can enable, with the right cooperation with the OEM, can enable a non-EGR architecture and can eliminate engine-based heating. So in this example down below for engine-based heating, oftentimes we'll see intake air throttling, we'll see exhaust air throttling, and some EGR. And you can remove those devices. You can let the engine out NOx go up considerably by doing that and get some efficiency gains from the pumping losses through the EGR system and put the heater in the aftertreatment system and let the aftertreatment system take care of itself. So fuel economy benefit from this is certainly realized, as well as offsetting the hardware that was on the engine. We took the 24-volt heater and we fashioned just a temporary structure of some cones so that we could put it in an exhaust system and do some testing with it. And we used the 24-volt power switch that I showed on the previous slide, and just did some simple work. It was 4.1 kW heater. We put this on a Cummins 7-liter engine, and we had the mass flow rate of 0.108 kilograms per second. And you can see, even with just a small heater, 4.1 kilograms, we're able to get close to a 30-degree C temperature rise. So you think about a 24-volt system. You can place this heater in front of the DOC, for example, and you can immediately get the DOC to rise in temperature and begin producing NO2 or begin fuel dosing if you wish to do an active regeneration. If we compare the new heater performance to the old heater performance on the same 7-liter engine, these are two different settings at 10% load and at 30% load. And you can see from the graph that the new heater plus the smart power switch can enable about 1.7 times higher temperature increase at any given point in that map, while reducing the size of the heater by well over 50%. So we've been able to greatly increase the output of the heater, reduce the package size, and as I mentioned, protect it from the overheating. So in conclusion, tightening regulations are demanding a reduction in CO2, NOx, and fuel consumption, and creating this increasing need for thermal energy in the SCR aftertreatment system. And so hopefully I've been able to show here today electric exhaust heating can provide benefits over traditional engine-based heating methods. And development efforts at Watlow have resulted in a much smaller and lower cost heating system. So we're excited about the work that we've done, and we see potential for this certainly in on-road vehicles as well as off-road vehicles that have 24 or 48-volt electrical systems. I'd just like to acknowledge a number of people at Watlow that contributed to the design, analysis, and testing of the various heating systems that we shared today. And then the references to our paper are listed here, and I'd be happy to answer any questions that you might have.
Thank you. Thank you, Jeff. So let's open to the floor for a few questions. And we have a question straight up on the right-hand side.
Yeah, hello, Frank Rother, TT Electronics. Just one short question. Where's the energy coming from you're using for your heating system? If you talk 30 kilowatt and considering 24 volt system, you would have more than 1000 ampere to handle. How to handle it and where does it come from?
Yes, so in the earlier slides, that was a diesel hybrid electric. You have a large generator attached to the engine and you're making, you have a 300 and some volt supply of electricity. In the later version, the 24 volt, we specifically aimed that at vehicles that have a 24 volt electrical system, or now we're seeing 48 volt systems coming in Europe and elsewhere. So that is powered from the alternator. In the case of 24 or 48 volts, it's powered from the alternator on the engine.
Just an extension of that question, have you compared the overall fuel efficiency between using your system, generating that power from the alternator and then heating the exhaust, compared with one of the alternatives like a seventh injector or a burner? How does the overall balance look on fuel efficiency?
Yes, so putting the heater in the system and removing, for example, inlet air throttling or in exhaust gas throttling, we see about a 2 to 3% fuel efficiency gain by putting the heater downstream. And a lot of that comes from the fact that we don't have the thermal losses all the way from the turbo outlet down to where the catalysts are. If we put the heater right next to where the heat is needed, we overcome all those thermal losses from the engine-based heating method.
Right. So if you had the heating method, the alternative heating method close to the after-treatment system, say with a seventh injector and the DOC, would that then be a similar overall energy impact? Because you don't have all the thermal losses on the exhaust.
Yep, so in the case of a burner, that's probably the most efficient conversion of fuel energy to thermal energy in the exhaust pipe. And certainly you're burning raw fuel, but there are many issues associated with a burner system, not the least of which is cost and the complexity of controlling it and the maintenance around it. So many people have elected not to use a burner system. In the case of fuel dosing, say a seventh injector with a DOC, certainly we're competitive with that from a fuel consumption standpoint with the exhaust-based, with the electric heater.
Oh, great. Okay, thank you. Any final questions? Otherwise, we should take a break. Any other questions? No, in that case, Jeff, thank you very much for a very detailed overview. Thank you. We are going to take a break, and because the schedule is tight to make sure you all have a dinner this evening, we're going to return at the planned time. So we'll come back here at 3:30. So have a 20-minute break, and we'll be back at 3:30. Very interesting final session, some great topics. So